So this is a very special episode of Struggling Grad Student. I am in Banff, Canada at a conference in convex geometry. I was invited late last week to come to Canada for this conference and I really wanted to go, so here I am. Today was my travel day. I got up at like 5 a.m. and I got here local time at like 5:30 and to the hotel, which feels more like 7:30. So, as you can imagine, I'm pretty dang tired. I just ate dinner at the mess hall, or banquet hall, I guess I should call it. And I really wanted to make a video because of how special this episode is. I guess I call it an episode, it's just a YouTube video. But I couldn't think of what to make. So I decided just to review what Lebesgue measure is, because I talk about Lebesgue measure a lot on the channel, and I don't know if I've ever really defined it. And I've basically just wrote down the important stuff. I didn't go down into the absolute, textbook level definitions of everything. So I just kind of wrote down a review of the notes, so to speak. So if you're taking measure theory at the moment, or probability theory or whatever, then this might be beneficial, as like a review. Plus, I said a long time ago that I was going to do a video series on measure theory, and I have not forgotten about that. It's kind of difficult to make excuses, basically, is what I'm doing. But it's still in the works. I still have everything to go. So I think the next maybe series of videos will be the measure theory series, because I do want to get that accomplished before all this stuff leaves my brain after passing qualifier. So anyway, let's talk about the Lebesgue measure. So here, we're going to talk about Lebesgue measure on the space RD, which is just the vector space of ordered pairs where there's D entries where each comes from the real numbers. That's a very bad way of defining RD, but I'm going to assume that you know what it is because I can't speak tonight, apparently. So the Lebesgue measure on RD. What is Lebesgue measure? Why do we care about it? What was its purpose in the beginning? The way I think of it is that in the one-dimensional case, if I ask you how big a set is, you would measure it in terms of length. If I want to say here's a number and here's another number, and I want to tell you how far apart they are, you have this notion of length. And in the two-dimensional case, if I had the plane, if I drew a circle or a square or any shape I want, I can ask you the question of what's its area. So area is a very natural way of describing how big a set is in the two-dimensional setting. And then for three-dimensionals, you have shapes like the cube and the ball and other three-dimensional shapes. It makes sense to talk about volume, and you can talk about d-dimensional volume. So the idea here is that we want to take that notion of volume and abstract it, make it more powerful. Because, for example, if I was interested in measuring the set of rational numbers on the real number line, how would I answer that question? Because what would its length be? And maybe you'll say it's infinite because there's infinitely many rational numbers and they're all over the place. You can always find a bigger rational number and a smaller one for that matter. So is it infinite or is it something else? What does this idea of volume tell us? So I think maybe at the end of the video, I'll explain, how to answer that question. Okay, so Lebesgue measure on RD. We start with the parallel pipette. So we have this rectangle, so to speak. Rectangle, parallel pipette, you can get the idea. What's the geometry term? Rectangular prism, I think, of D intervals. So here's my first interval, second, so on and so forth. And I take the Cartesian product and I look at this set. If it was the three-dimensional case, then I would have three of these guys, and if I wanted to measure the volume, all I would do is just measure the length of each side and multiply them together. So I need the length of this interval times the length of that interval times the length of these intervals up to this amount. And so I can generalize that by saying the d-dimensional volume of P, the parallel pipette, is just the product of absolute value of BI minus AI, and there's D of them. So that's kind of a natural notion of how the volume of a parallel pipette is. So you start there. And then we say, okay, I want to use this to figure out how to measure the volume of any set that's in RD. You know, how do I measure the d-dimensional volume of E? Because like I said, if you consider like QD, where you have Q raised to the D, where each entry in the ordered pair is a rational number, how would you do that? Okay, so the way it's done is you define this new set function called MD star. The inputs are sets in RD, so this denotes the power set. So you look at the set of all subsets of RD. So an input is a set, and it outputs a non-negative number. We're not really interested in negative numbers. There does exist measures that take on negative values called sign measures, but that goes beyond the scope of the video. So it makes sense to only consider non-negative numbers because, you know, if you ask someone what the volume of a cube is, you don't want them to say it's -2. That makes no sense. So we start with this function and we define it as follows. So we say that MD star of any set E is the infimum of the set of all numbers that satisfy this. So it's the sum of d-dimensional volumes of Pn, where these Pn's are parallelepipeds, like up before, such that E is a subset of the union of parallelepipeds. So what does this mean in plain, simple English? We take a bunch of parallelepipeds. We union them together such that they cover E. So if E is this blob, I basically draw a bunch of squares around the blob to cover the set E. And then instead of just measuring E directly, because we don't know how to do that, we instead just measure the volume of each parallelepiped. So we look at each of those squares or cubes or whatever we had, find their volumes and say, okay, we're going to say that E, the volume of E, is roughly the sum of those volumes of the parallelepipeds. But the problem is that you can choose many different covers of E. You know, you can choose really tiny squares and use a bunch of them, or you can just do one big square, or in the trivial case, you can just take the whole space RD if you allow A and B. The A's and B's appear to be infinity and negative infinity. But then that gives you multiple different answers, in which case you don't have a function. So the idea is that you want to cover E, and you want to find the smallest possible cover that you can. Smallest in terms of volume. And that's how you want to talk about MD star of E. And the reason it's called MD star of E is because it's called the D-dimensional, because we're in the space RD. If it's too hard to think about, just think of D as like 1, in which case you're just measuring stuff on the line. Or if you want something more abstract, just put 2 here, and then you're measuring sets on the plane. So it's called the D-dimensional Lebesgue outer measure of RD. The name Lebesgue comes from the French mathematician Henri Lebesgue, and this is his big namesake. So we call this MD star the Lebesgue outer measure. If it's obvious what the dimension is, then they don't even write this part, and sometimes they omit the D and just call it the Lebesgue outer measure. And the Lebesgue outer measure has 3 interesting properties. So these are the 3 properties. The first property says that if you measure the empty set, then its size better be 0, which kind of makes sense. If I have a set with nothing in it, it makes sense for that set to have weight 0, if you want to think of it that way. The second property says that if I have a subset of another set, then the measure, the outer measure of A, has to be less than or equal to the outer measure of the bigger set, which makes sense, right? If A was me as an 8-year-old and B is me as an 18-year-old, then my height as an 8-year-old better be smaller than or equal to my height as an 18-year-old. And this is called the monotonicity property. If sets get bigger, their volumes better get bigger as well. And then the third property is called countable subadditivity, which says that if I take any collection of sets, even if it's infinite, countably infinite, then the Lebesgue outer measure of its union is less than or equal to the sum of the Lebesgue outer measures of each individual piece. And that should make sense. because it's like saying if I'm interested in, measuring a person's weight. I don't know. No, let's do it a different way. Let's say that I'm interested in measuring like a honeydew or something. I say honeydew because I had honeydew the other day. If I'm interested in measuring that honeydew, then if I chop it up into little pieces and then add up the weights of the pieces, it better be greater than or equal to the union of all those honeydew pieces. And the example I've given here isn't very good, because in the example of the honeydew, I've split it up into separate pieces. So I have a piece here, piece here, piece here, piece here. But these sets here can overlap. So just to draw a picture, like let's do something very basic. If I draw a circle and then I draw another circle that overlaps it, and I want to know the area that's covered by the two circles, one way to do it is to find the area of one circle and then add it to the area of the other circle. But the problem is that you count this area in between the two circles twice. And that's where the greater than equal to sign comes into play. And the intuition here is that if they're separate, like this, then you'll have equality. The problem is that for some sets, that works for the outer measure, like the outer measure can do that. But there are sets out there that even if the two sets are separated, then the outer measure can't do it. You don't have the fourth property, which says that if I have a disjoint collection of sets, meaning no overlaps, then the outer measure of the union is not necessarily equal to the sum of the outer measures. And that's the fourth property that takes us from outer measure to the Lebesgue measure. So there's a couple different ways that textbooks like to approach it, and this is kind of the way I like to remember it. So because exist bad sets, and by the way, these sets are not easy to explain. They're very complicated sets. If you're interested in reading about them, look up Vitali sets on Wikipedia. But basically, those sets are bad, and we want to get rid of those sets. But we want to keep the good sets, meaning the sets that have this property here, and we want to be able to play around with them without accidentally creating bad sets from them. So this is where the idea of the well-separating principle comes from. If you want to look this up on the internet, it's called the Carathéodory theorem. And I'll write it here because it is kind of complicated to spell. Carathéodory. And I believe there's a accent on the E for Carathéodory. So the idea is that you take this outer measure and you restrict it to the set of all well-separating sets. And I denote the set of all well-separating sets as fancy M. But what does well-separating mean? Well-separating means that if I take any subset from RD, so we're saying E is well-separating, you take any set from you take any set A from RD, and then the Lebesgue outer measure of A can be written as the Lebesgue outer measure of A that's inside of E plus the Lebesgue outer measure of A that's outside of E. So you look at the piece of A that's inside E and the piece of A that's outside of E. And if you can add those two up to get the Lebesgue outer measure of A, then you say E is well separating. And then you collect all the sets E that have this property and you put them into fancy M. And I did not write it here, but you can show that fancy M is what's called a sigma algebra, which means that if you union two well-separating sets, it remains well-separating. If you take the intersection of two well-separating sets, it remains well-separating. And it also works for complements. So if you take one, complement it from the other, and vice versa, it still stays well-separating. Look up sigma algebra on the internet and you'll see what I mean. So you take this set function, MD, and you restrict it to this set of well-separating sets. And then this MD, which I denote, is called the Lebesgue measure on RD. And the Lebesgue measure on RD is our generalized notion of volume, so to speak. It's probably the most famous measure. Second, or not second, but the second place would probably be like the counting measure or something. Okay. So, what can we use the Lebesgue outer measure, not Lebesgue outer measure, but Lebesgue measure for? I can't remember if I talked about this in a previous video, so I'm going to talk about it here. The idea is that I want to find the length, or find the one-dimensional Lebesgue measure of Q, being the set of all rational numbers. So because the Lebesgue outer measure, or excuse me, because Q is countable, this means that we can write Q as a list. We can write it as a list. And then we cover each of these Q's with an interval. So cover Q sub n with the following interval. So the interval is Qn minus epsilon over 2 to the n plus 1 power Qn plus epsilon over 2 to the n plus 1 power, where epsilon positive is given. I should have written that first, so forgive me. I created the cardinal sin of analysts as I did not start with our adage, let epsilon be given, and then write everything else. But we take each, so what does this interval mean? It means that you take an interval, you center it at Qn, and you go out this amount this way, and you go out that amount that way. So that the volume, the one-dimensional volume of this interval, which I'll call I sub n, is equal to 2 times epsilon over 2 to the n plus 1, which is just epsilon over 2 to the n. Okay? So this is multiplication. And the one-dimensional volume here is just length in this case. So then we see that Q is a subset of the union of all these guys. Well, I should have just wrote IN. I have the notation. I should use it. And then I use the countable subadditivity property. So we know that the measure, whatever it is, of Q has to be bounded below by 0 by definition. But by countable subadditivity, it's bounded above by the sum of the measure, one-dimensional measure. I should put 1 here, of IN, n equal 1 to infinity. And that is less than or equal to the sum of these boys, epsilon over 2 to the n. All I did was replace this with what its measure is. And the epsilon can be carried out, so that's equal to epsilon sum 1 over 2 to the n equal 1 to infinity. And this is a geometric series, and that geometric series tends to 1. So we end up with the measure of Q is bounded above by epsilon. And because epsilon is a positive number and an arbitrary positive number, it means that we can make epsilon as small as we want, which means that the measure of Q has to be smaller than any positive number that we pick. And because it's bounded below by 0, this is enough to conclude that the Lebesgue measure of Q is equal to 0. And I can leave it to you as an exercise to show, the YouTuber leaves it as an exercise to the viewer, that the measure of QD in d-dimensional space with the d-dimensional Lebesgue measure is in fact 0 every time. And that stems from the fact that Q is countable. And it doesn't matter Q2, Q3, Q and 19, however big a dimension you want, it remains countable every time. So the one-dimensional Lebesgue measure of the rational numbers is 0. Okay. I am really tired. I am really thirsty. I want to go to bed, so goodbye.